Okay, so good evening, everyone. Welcome to Cloud Collective, today's meetup. So I'm your host, Praveen Salitra. If I can control my slides remotely. Yeah, I'm your host, Praveen Salitra, Head of Technology here at Egen. We are a cloud native services company here in one of the suburbs of Chicago. So we are here technically in Naperville. And I think it has been probably 3 months or so that we are restarting the meetups again. We have almost 4 weeks of content lined up for you. So not just today, but then every Thursday going forward for the next 4 weeks. Hopefully, we can continue doing that for the next few weeks as well, not just next four. So, who is Egen? Egen is a data engineering and cloud modernization firm based out of here in the Chicagoland area. Uh, we actually started working 6 years ago with some of the startups in Chicago, and that became a very well-known startups down the line or today at this point. And throughout this time and history with some of the startups, working with them on a lot of new cool platforms for the first time in the world, for example, in industrial IoT, in some cases in healthcare, in retail, with some enterprises now. We have understood a lot of things with respect to either data engineering, if you talk about it, cloud infrastructure, or even applications and things like that. So, what we do in this kind of meetups is we share all those learnings to the public, to the community. At Egen, as I said, across our projects in the last few years, we have gained domain expertise and understanding of industrial IoT, the industry or the domain which didn't even exist before 2014, I think. And of course, healthcare. A couple of our bigger projects are on the healthcare side, working with some of the partners there. And then, of course, in the last 2.5 years, mostly working with the retail as well. At this point, 10 to 15 different projects of different sizes and scale, whether it's dealing with some enterprises, helping them modernize to the cloud, but then also re-architect the platform. So that has been some of our major projects at this point, working with the clients. We have been working with some entrepreneurs as well from Chicago. They have an idea, and we help them build the idea, release it to the market in the 3 months kind of a time period. So that's launching their idea, and then also when someone has already, or a startup has already tested their product market fit, we help them scale and go from there. So across all of our projects, the engineering principles are still the same or kind of similar, whether it's starting from the event-driven architecture. We love Apache Kafka, have been using it for almost 6 years now, or using modern data pipelines and going through the concepts of microservices, utilizing serverless or managed services as much as we can, mostly from the cloud providers. Automation, not just in terms of CI, CD, or test, but then also the entire observability stack. And then, of course, mostly utilizing either the cloud managed services or open source frameworks. That has been one of the key set of engineering principles that we have here at Egen. And that, of course, makes us utilize a lot of technical stacks and programming stacks as well, whether it's just using TypeScript or JavaScript stack end to end on some of our projects, whether not just on the mobile apps or the web apps, but then also onto the RESTful APIs and GraphQL APIs and other services as well, using some flavor of Node.js framework. Of course, traditionally heavy on the statically typed languages as well, or more popular enterprise languages as well, if you can call them, whether it's Java, whether it's Python, whether it's .NET. We have been experimenting with Go in our DevOps scenario as well. But in the last few years, I would say 2 years or so, most of our new client engagements are mostly because of our data engineering expertise and cloud engineering expertise as well. So that's pretty much it about what we do here at Egen. If you are interested in working with us or even knowing what we are doing here, of course, one option is to probably look out for job opportunities here at Egen. We are here in Naperville, so you can head over to egen.solutions/careers, and then I'm sure you will find technical, non-technical product or any other sort of function as well, and you will be able to find a job posting available out there. So please apply. We go through a couple of rounds of interviews, all Zoom this time, of course, and then one final call as well. In the starting phase, we may have some sort of automated test, or we may give some sort of take-home exercises as well. So work with our recruiting team, and you can apply on the link which is available there. So let's jump into what do we have for today. So today we again have Arif, one of our software engineer here at Egen. He has been working with us for almost now 2 years. Have been working on a retail project, a grocery retail project. And today he's going to be talking about how to build reactive systems with Spring and Project Reactor. So let's see what Arif has to say. So over to you, Arif.
All right. Thank you, Praveen. And thank you all for joining in today. Again, my name is Arif, and I love backend systems development. And as Praveen mentioned recently, one of our projects in our team, we came across this new concept of reactive system. And today, I'm going to use this platform of collective meetups to share some of the learnings with you all. And but before we talk about building reactive systems or the added advantages of reactive systems, I want to take a step back and do a brief recap onto the current industry standard, right? And we'd go from there. We'd try to nitpick some of the problems with the current system, and then introduce the reactive systems in a way that we better understand the advantages and the need for the reactive system, right? So let's start there. I'm sure all of us here are familiar with the points in this slide, so I'm going to breeze over them. Stateless APIs don't carry any state information, and all the requests coming into a stateless API are independent of each other, so they can be served by any instance of the same service. So we can have multiple instances of the same service running behind the load balancer, which can distribute these requests to any of the service running. And similarly, what happens when you have this kind of setup is you can scale the number of instances as you go. As in, if you have high traffic, you can scale the number of instances up. If you have low traffic, you can scale it down. Also called as auto scaling. So stateless APIs and auto scaling go hand in hand. This setup on cloud is of course very useful, because then you are by definition just paying for what you use, right? So if the traffic is high, you're increasing the number of resources, you're paying extra for that. But then as soon as the traffic goes down, you cut it down, and then you're not paying that extra money. That is all good. Now, the preferred choice for backend systems development in the enterprise world today is Java and Spring Boot, probably because both of them are free. Java is free to use. Spring Boot is an open source system, so free to use. So companies love to use these two in conjunction with each other. Also because Spring Boot is an amazing framework that makes stuff easy. And for those of you who are not familiar with Spring Boot, again, as I mentioned, it's a great framework. It does all the work that developers hate and probably should not be doing in the first place. So all the configurations and setting things up, all of that is done by Spring Boot. For example, if I were to write a REST API, I know all REST APIs that I write need a JSON parser. They need a Tomcat server to run on. And the Pivotal team, the Spring team actually at Pivotal came up with this idea that why not we just centralize all of these configurations and let the developers do what matters most, writing the business logic, solving the business problem, right? And that is what we love to do, apart from all of these configurations, of course. So Spring Boot, again, is a very good framework to do all of that and straight in to get straight up building REST APIs end to end. Now, yeah, this is been an industry norm for a long time. So what is wrong with this model, right? It's great, it works, and there's no evident problem with it right now. So as I mentioned earlier, we are going to nitpick on a few problems, and then we'll see how reactive systems make the most impact, right? So let's first talk about the Tomcat request model. So traditionally, Tomcat's request model has been a thread per request model, meaning each request that comes into the app is carried out on a separate individual thread of its own. So if I send an application, if I send a request to my application, it will be completed end to end, right from the inception of the request to the return of the request on one single individual thread, right? So the number of requests is equal to number of threads. More requests, meaning Tomcat will create more threads. And that is good, right? Parallelism. You are trying to execute all threads individually by themselves in a parallel fashion. Parallelism is great. But is it? Yes, so parallelism is good, but up to a certain extent only. So for the sake of simplicity, let's say you are running an application directly on a 4-core machine, right? There's no virtualization, again, for sake of simplicity. There will be virtualization, of course, in the real world out there, but let's say you're running this application on a 4-core machine directly. So when you have 4 requests simultaneously coming in, Tomcat spins 4 threads, and these 4 threads can independently work on the 4 cores, right? But what happens if there is an increase in the number of threads? What if you have more requests coming in? And what if there is more than 4 threads, right? Say 100 threads, for example. In that case, the operating system does something that is called as context switch. So if we go back to our operating systems class from our bachelor's or master's in computer science, context switching is a very neat trick performed by the operating system, which gives us the illusion of parallelism, right? But in reality, it's still doing the job sequentially by actually dividing the time of the CPU in something called as slices. So the operating system divides the CPU time into time slices, and then periodically, in some fashion, usually round robin, it divides these time slices to the threads, right? So each thread gets its own time slice after a certain period of time, and then the thread can execute on that time slice, and things go accordingly. So again, this is the model. There is no evident problem with this because this has been working for about 20 years now in the enterprise world, and nobody seems to have any problems with it. Even right now, if you see the most modern architectures with Spring Boot, the latest version, what you see is this, exactly this. The thread per request model is very successful. There's no evident problems with it. But as I mentioned again, we are going to nitpick. We are going to find the problem here. So let's see, what does a thread do when it processes a request, right? So anytime a thread is processing a request, the work that a thread does can be broadly categorized into just 2 parts. The first part is performing business logic, right? So business logic meaning anything which is internal to your system. As long as you're not leaving this API and going outside, that's just business logic. And the second piece of it is input output. So anything that leaves your system and goes outside the system is basically input output. So it can be your database calls, it can be calls to your external API, anything like that. All right. So within these 2 pieces, the IO piece, right, the input output piece is pretty expensive and can be unreliable at certain times, right? It can take nanoseconds in some cases to minutes, right? I've seen some cases where the services are really bad, and because of the network latency and various other factors, the input output can sometimes take a lot of time. So even minutes, it can reach minutes. So let's assume in this case, for the sake of simplicity, let's assume the worst and say that we have an application that is taking about 30 seconds for each IO request. So whenever we make an IO request from our application to a database, it's taking about 30 seconds, right? So what happens to the thread while it is waiting for this IO for 30 seconds? What does the thread do within that 30 seconds? And the answer is the thread does absolutely nothing. It as stated, just waits for the IO to finish. And in other terms, it is a blocking call. Your thread is blocked, doing nothing for the 30 seconds that it waits for the IO, which is not good, right? And the 30-second wastage here, if you go back to our context switching point, the CPU, the operating system, doesn't know that the thread is waiting. The operating system will do its job and provide the thread with a time slice whenever the time comes for that thread. And the thread will take that time slice and again, absolutely do nothing within that 30 seconds, effectively just wasting that time slice, right? And CPU time slices are precious resources. You cannot be wasting them like that, right? Of course, the 30-second point here is exaggerated, and it's not always 30 seconds. But if we talk about CPU wastage over a long period of time, say over a year, it eventually adds up, right? Even if it is a small amount of wastage, say you're wasting a few milliseconds on each request, eventually over a period of time, it will add up. And if we are talking things on cloud, we pay for that money. Anything that you do on cloud, anytime you waste with CPU resources is money wasted. And if you talk about something like, say, AWS Lambda, which is a true serverless and true pay-per-use technology, they calculate costs based on your CPU usage. Think about that, and think about an application which is waiting for IO and just wasting CPU memory resources. Now, AWS is billing you for those for the period of time you are just sitting and waiting for IO to finish, which is not ideal, right? And that is a problem. So now we've established the problem. Let's talk about the solution, right? So what is the solution? Of course, it is reactive systems, and I feel we could have better created the suspense if it weren't for the title of the meetup, right? And come to this grand conclusion that reactive systems is the answer. But we all know reactive systems is the answer, and all of this build up for was for getting into that. So let's talk about reactive systems, right? So what are reactive systems, you ask? Very simply put, any system which is not blocked or does not wait for IO to finish, right? So if it does not wait for IO to finish, how does it work? So firstly, we will have a very small size of thread pool. We don't have unlimited threads to work with. We will have a very small size of thread pool. And then when a request comes in, one of these empty threads from the pool can accept this request and process it. And as soon as the thread encounters any sort of IO where it has to wait, what it does, it will register a callback and returns to the empty thread pool again. We'll see that in more detail in the upcoming slides. But just think of this as registering a callback and returning to the thread pool. So what happens after it returns? Now that the thread has returned, it can now take in new requests, and it can process those new requests, right? What about the unfinished IO? As soon as the IO finishes, that callback function again calls the empty thread pool back, and another free thread or that same free thread, doesn't matter. Someone from that thread pool is going to take the remainder of the request and execute the remaining portion, right? So it's very simple. You just don't wait for IO. You register a callback, and the callback triggers whenever the IO is done. Back to the thread pool, someone from the thread pool will take the remainder of the work and do it for you. Okay, so that is really the answer to all of this. And I know a lot of you would here would be like, all of this is great, non-blocking IO, and it sounds interesting, but who would do this work, right? It is a lot of work, a lot of groundwork implementing this sort of thing, where you have to register callbacks, configure a thread pool, talk to the operating system for managing these threads and stuff like that. And as application level programmers, we're trying to solve business problems. We're trying to drive the business forward, and trying to make money for our enterprises. And we don't really have time for doing all of this, right? And it is also repetitive work, as in, if you are to do this for multiple different services and multiple different APIs, you have to do the same thing all over again. And that kind of sounds familiar, right? From our conversation about Spring Boot earlier, or that at least sounded familiar to the Spring team. And what they did was exactly what they did with Spring Boot. They took all of this and made it into a solid framework so that we don't have to do any ground level work. And us as developers can reap all the benefits of having a reactive system, and just do the application level programming. Also, to sweeten all of this up, the Spring team, they kept this the application interface exactly as Spring Boot. So the Spring Boot that we have all come to love is exactly the same. It's just adding new dependencies, with a few exception of a few new data structures, which we'll discuss, which actually bring in the reactive component. So a lot of the things remain same, except for a few things that have come in new, and we'll see those new things and how to use them. So the point I'm trying to make here is that the learning curve here is not as big as you'd think. Okay, and yeah, so just like the older Spring Boot versions, it is now possible to build fully async non-blocking reactive APIs end-to-end with the Spring Webflux. And then, needless to say, we would now be utilizing the resources to its fullest, and hence we could scale better within the given resources. What we're doing previously is we were scaling, right? but we were scaling by adding instances. Now we're using the same instance and using it to its fullest true potential, and scaling within that same ecosystem. So of course, horizontal scaling is here to stay and it's not going anywhere. This is sort of scaling within the given amount of resources, and this is also here to stay. It'll make a big impact in the future. Okay, coming to this diagram, it's a very popular reactive event loop diagram that you might have seen with different programming stacks and languages. It's very simple. So the word request has here been changed with event. So anytime there's an event, it goes to the thread pool, registers a callback, does not wait for the database layer, and then whenever the IO finishes, the callback is executed. It goes back to the thread pool or the event loop, and then the process continues from there. I haven't done a lot of JavaScript, but from my talks with my fellow Egen engineers and Praveen, I've come to an understanding that Node.js uses a similar model on the backend. The only difference being Node.js would be a single threaded application, whereas with Spring Boot, you can configure the number of threads you're going to use. If you don't configure it, Spring is very smart and it will take the default number of cores allotted to the application as the default number of threads. But if you don't configure, but if you're good at threading and you want to get into the nitty-gritty details of threads, you can configure the thread pool by yourself. Cool. Okay, this is interesting. So on the screen, you see the reactive stack diagram, right? And the tagline says either fully reactive or blocking, nothing in between. So when you're married to the idea of say going reactive, right, you've got to be faithful to that idea. You cannot have blocking calls anywhere in your stack. You have to be reactive all the way because by definition, right, if you're doing non-blocking stuff and somewhere down the stream you make one blocking call, it's not going to work because then you're blocking the thread. So the Spring team realized this, and they came up with an entire stack which would support the reactive model, right? Starting up with Netty on top. Netty is a server replacement for Tomcat. Tomcat is blocking in nature. Netty is fully compatible with non-blocking IO and is developed by Netty is an open source community project, so it is maintained by a lot of people. And then we have Servlet 3.1 specification that came out in Java 7 EE that supported non-blocking IO fully. So Servlet 3.1, and then we have reactive stream adapter. So Netty and Servlet 3.1, sorry. Servlet 3.1 is a non-blocking specification written in Java. And then what we have with Spring is based on Project Reactor, which we'll talk about in the next slide. But Project Reactor is a little different in terms of it's still non-blocking, right? It's still reactive, but it works a little differently than what Servlet 3.1 has defined. So we need a bridge sort of in between to bridge the gap between the non-blocking IO of Java and non-blocking IO of Spring. So that is where the stream adapters come in. And then there's Spring Security Reactive. So Spring Security is a component that sits on top of Spring MVC, regular Spring MVC. So if we were to do the Webflux, the reactive MVC, we would need something that replaces Spring Security. So the Spring team added Spring Security Reactive. Then came in Spring Webflux, of course, and then at the database layer we have something called R2DBC, which is again fully non-blocking way to connect to the database. A lot of support is now available with R2DBC to connect to a lot of variety of databases. So that is all in all the entire stack, the reactive stack. And over on the right side, you can see the non-reactive stack, which is Servlet API, Spring Security, Spring MVC, and then finally our favorite Spring Data JPA, right? Very easy to use, and all of these systems on the right are matured. The ones on the left are upcoming, new, and very interesting, I should say. Cool. So well, let's talk about the history of it all and a little bit about Project Reactor as well that I just mentioned briefly in the last slide. So what happened is back in 2013, a group of very smart people from Netflix Pivotal and Lightbend. These guys, they're probably getting coffee in Bay Area, and they met on Starbucks, and they were just talking among themselves and like, let's revolutionize this thing, man. The backend systems, they're blocking calls, and it doesn't make sense to wait for IO, right? So they came up with this holy reactive specification. So this reactive specification is just a bunch of not even a bunch. It is just collection of four interfaces that define how the reactive streams would work, right? And those four classes are publisher, subscriber, processor, and subscription. And we'll talk about them when we go to the live demo of it. But this reactive specification was then taken by Netflix, Pivotal, and Lightbend in their own ways and extended in different projects. And these different projects can now talk to each other because they're on the same specification. They're on the same reactive specification. So the data flow between these projects is possible. Pivotal, interestingly, what they did with this project is they extended it to be the Project Reactor. So Project Reactor, the main aim of Project Reactor is to add high-level operation support on top of the reactive specification. Now, if I say there is these classes, publisher, subscriber, and whatever, go use them. It's not easy, right? Because we've come to a point in programming languages where we are used to having higher level operations like, say, map, flat map, for each, stuff like that, right? So Project Reactor's main aim was to give you the high level operations that can be performed on these reactive streams. So reactive streams are in many ways similar to your Java 8 streams, with just one exception, that Java 8 streams are synchronous and work with util collections. Reactive streams are asynchronous. They are non-blocking and don't work with util collections. Rather, they work with special data types, which will come to Flux and Mono little later in the demo. So that was the aim of Project Reactor. But is that enough, right? Project Reactor, if I give you Project Reactor and tell you to build a Spring REST API, is that enough? Of course not. So the Spring team is motivated, or was motivated, to come up with a framework again that could be used end-to-end to build REST APIs in non-blocking fashion. So their Spring Framework 5 was born. Along with it, they introduced Spring Boot with Webflux and R2DBC, Spring Reactive, and many other Spring applications that announced support for fully reactive, non-blocking end-to-end systems. And then this gives us the ability to build reactive systems end-to-end, right? Cool. We've come to the demo part. So I'll stop sharing here for a while and set that up for us. And we can quickly go through the demo here, guys. Okay. All right. So I have this project in here. It's called the car tracker, right? And I'll take you through the controller, or rather I'll just run this project, okay? And we can see the Swagger, and I'll go through the Swagger to just show you what exactly is happening here, okay? So the project is booting up now. Okay, cool. So this is a regular Spring Boot project with all the starter Spring Boot dependencies, and I've configured OpenAPI 3 for this. So if I were to go to localhost 8080 Swagger, what happened there? As I was running on 8081, for some reason I configured it on 8081 and forgot about that. So let me make those 8081. Okay, here we are. We have the vehicles controller, reading controller, and alert controller. Very quick overview. It is a project that kind of does in IoT, Internet of Things. you have vehicles and sensors within the vehicles sending you readings each time. So you can register your vehicles here first, and this is connected to a Postgres database in the backend. And then you have readings controller, so that takes in the readings from the sensors. And then what happens is, if these readings coming in from the sensors indicate some sort of something that is wrong with the vehicle, we create an alert and store it as an alert in the backend as well, which we'll see in the API. But again, high level overview: with the vehicles controller, we register vehicles. With the readings controller, we pass in readings, and if the readings have some metrics that are bad, we create an alert and store the alert in as well. So I think I have a few vehicles registered already. No, I don't. So let me register vehicles here. I have a very quick JSON here, which I will use to add these vehicles in. So I'm using a put endpoint, and there we go. So we get the 200 back, just to check if we have those in there. Yeah, so these two are now registered. And then we can send a reading in. So if I were to send this reading along, I also have a very quick example for a reading interface here, and then take this and post it here. Okay, this is all just set up, guys. Okay, so we get a 200 back. We have that reading added in there as well, right? So this is how the regular Spring Boot project would look like. You would have a controller which goes evidently into the service layer, right? You have the service implementation which goes into the repository, and then we are using the famous JPA repository here, which gives us all the nice features to do find all. All of these are implemented by Spring Data JPA, so we don't have to worry about them. And it's a very sweet interface, right? Because you don't have to write queries anymore. So we are going to try and convert this project into a Webflux project. So notice this is a JPA repository, which basically means it is a blocking repository. Any call made to the JPA repository, the thread will wait until the JPA repository returns an answer, and we don't want to do that. So what we'll do is we'll convert this project into a Webflux project, right? And try and see what happens. So right here we can see we have Spring Boot data started data JPA, started dependency for data JPA, and then started dependency for web. And then we have something for Swagger in here, Lombok, Postgres SQL driver, and then annotation processor. So very simple. Instead of data JPA, what we want is R2DBC. That's it. That's your driver, R2DBC dependency, and we want Webflux. I am going to just double check. Yes. So Webflux is your dependency for getting the web component, or it's a direct replacement for Spring Web, Starter Web. And then R2DBC is your direct replacement for Spring Data JPA. Okay. Also, you'll have to change the driver that you use for Postgres. So instead of the traditional Postgres SQL driver, we're going to add the R2DBC compliant driver, which again is here. Where is it? Here. We're going to take that and add that. Now that we have all of that, and it is interesting to note that Swagger will actually have to be changed as well. So there is an implementation that is compatible with Swagger implementation that is compatible with the Webflux or Reactive Spring Boot, and that is the dependency for that, right? So once we've changed all these dependencies, let's quickly let Gradle do its job and refresh so that we see a bunch of different errors that we can solve. And straight away, we'll go into the repositories, right? So vehicle repository, let's go there. And let's wait for IntelliJ to refresh the libraries here. Okay. Now that JPA is gone, we of course cannot use the JPA repository. So what we are going to use is the direct replacement, right? So this is the direct replacement. You don't have to change anything except this one class. We are going to use the reactive CRUD repository. See how easy it is. This is what I meant when I told you guys that the Spring Boot that we love remains the same. So all of these classes and how it works remains the same, except for a few new classes and a few new things here and there. Okay. So if I were to go into the reactive CRUD repository, you can see that anything that's find by ID or anything that you try to do you try to get the data from the database, it returns a mono, or in some cases it can return a flux, right? So these are two data types that we want to discuss here for a little bit. So if I were to go into Flux, right? Flux is extending a core publisher, which is in turn extending the publisher, which comes from the reactive streams specification. This is what I talked about earlier within the presentation. So a publisher is defined in reactive stream specification, only has one method called subscribe. So that is one of your data types. And then there is a core publisher, which comes from Project Reactor, I think. Yeah, so it comes from Project Reactor. So Project Reactor, as I said, tries to build on top of the reactive specification. And then finally, they define Flux, right? Which is a core publisher, and then give you all these methods that you would expect from a high-level API. So combine last, I'm sure there's map and flat map in there, concat, stuff like that, right? Stuff that we're all very used to in this modern day programming language world, right? So that is that. We have Flux, and then we have Mono. Again, Mono is also a core publisher, and it extends a publisher as well. So what is the difference between the two? It is very simple. Mono is when you know that you're going to only get one object of any type back from your call, right? Flux is when you don't know how many objects you're going to get back. So Flux is basically, assume Flux to be a sort of a list, right? It is not actually a list. It is a stream of asynchronous events, but assume it to be a list sort of. So the direct comparison would be in synchronous terms, a list of objects, and then mono is just a single element, right? So when you know you are expecting just one object, you would use a mono. And then when you're expecting more than one object, you'd be using a Flux in that case. So that is your mono and Flux. Let's also change. So let's first change all repositories, right? And here again, I do a reactive CRUD repository. And again, all of this will remain the same. Here you can see I have a query, and it works exactly the same way with R2DBC as it did with Spring Data JPA. Same thing in alerts repository. To take that off. Just a second. So that is our repositories, right? Now you would naturally progress to the service layer, but I want to do it a little differently. Let's go to the controller, right? So with Spring, right? When I say that this method would return a vehicle, where does this return go to, right? This return goes back to the client, but it goes via the server. So now I'm going to return this vehicle, but I'm going to return it back to Netty in this case, and then Netty will return it back to the client. So I'm going to do a mono here, right? And again, Netty servlet 3.1 fully compatible with non-blocking IO. There's a adapter in between that will take this mono and convert it into the non-blocking IO of Netty, right? So mono, and then if there's a list, I will do a Flux, and then a Flux here, right? And of course, naturally, Spring Boot would start complaining because as you can see here, it says service find by ID of win, right? So this interface also needs to be changed. If there's only one return type, then I do a mono, and of course, change the list to a Flux there, right? And then the implementation needs to also change. So we're doing mono. And see how seamless this is. Okay, this returns a flux. Oh, sorry, we did a mono on the wrong thing. So this is a flux. It is find all. And again, find all in R2DBC reactive CRUD repository returns a flux, which is of course very good for us. And then again, we have a list. So we'll do a flux. And then again, save all also returns a flux. Great for us. Vehicle would return a mono of vehicle. And then you wouldn't do null. This would return a mono. Okay. And then let's go back. That was the vehicles controller. Let's do the same for alert controller. I'm going to go a little quick here so that we can go to the service layer where I want to discuss a few things as well. So both of these are flux, and alerts, flux. That implementation, flux. Okay. Cool. So that is all the controllers, I think. No. No freedoms. Flux. Flux. On this thing here. Okay. So we are now at the service layer. And remember from our conversation back when I was doing the Swagger thing, I told you that when a reading comes in, what the business logic of this particular API is to check for readings that that can give us an alert, right? So if there is a car whose red line RPM is going way above its limit, then we create an alert. If the tire pressure of a car falls below a certain threshold, we create an alert. Stuff like that, right? So quickly take you through the add readings method. What we do is as soon as a reading comes in, we try to find the vehicle using the VIN of the vehicle from the database. And then once we have that vehicle, we check for the RPM, fuel volume. So if the fuel gets down by a certain threshold, we have to create an alert and save it. And then also the tire pressure alert, check engine light on alert. So we have a few alerts here, right? And we want to, again, make all of these calls non-blocking. Here you can see you have multiple database calls, right? So first one is to try and find the vehicle from the database, then store this alert, and then finally store the reading as well. So the reactive way of doing it would be to take the vehicle, right? And this would return what? A mono of vehicle, right? Right. So now how do you work with this mono, right? We still have to do all of these things, but we have to work with a mono now instead of a regular object. So let's think of this in terms of a stream, right? What would you do if this was a regular Java stream? We would do this, right? We would do this vehicle dot map, right? So that we get the value of this vehicle, and then say actually name it vehicle, yeah, and do that. And then with this vehicle now you can perform all of these functions, right? So if I were to copy this here and just replace all of this with vehicle instead of this vehicle, right? Now it makes sense because we are now treating this as a stream, and the first object we get from the stream, we're going to take that object and then do all of these operations. Now, similar to Java streams, this is a cold stream, cold pipeline, as in it wouldn't execute unless I subscribe to this or I start this by a terminal operation, right? So are we going to do that terminal operation? No, not yet. So first thing is we are going to return a mono. So we are going to return that stream, right? We're not going to start this stream. So who starts this stream and who executes this? We'll come to that in a while, but let's just complete the execution first. So this vehicle.map, so we have mapped it. So we also need to return this after the mapping. So we're not actually doing anything with the vehicle, but just using its value. So I'm going to simply say return vehicle here. Oh, not here, maybe here. Where does this finish? Okay, yeah, so here, okay. And then we close the map here. Now that we have done this piece of logic, right? The next thing here, we're saving all of these things, right? Which are again asynchronous calls, so we need not worry about all of these things. We are now going to save the readings, which is interesting. So let's say there is a situation where you want to save the readings only after you have done all of this process, right? So what do you do in that case? How do you make sure that this executes first and only then you save the readings in that? And with reactive, as you know, we are dealing here with threads and asynchronous patterns. It is not guaranteed that this piece of code, just because you've written it on top of this, will execute before this piece of code, right? It could execute on a different thread at a different time anywhere imaginable, right? So how do you make sure that happens, right? So there's two ways of doing that. You can do .block, right? Which, as the name suggests, will block this piece of code and execute this first, and only once you get the answer to this, right, whatever this would return, is when you execute the next piece of code, which is of course not what we want, right? We don't want to block anything, because as I mentioned earlier, it has to be reactive all the way through. You cannot have something which is blocking the thread and then call it reactive, right? So again, Project Reactor comes in to help here, and then you have functions like then, right? So you can specify what do you want to do after you've completed this operation. So you do a then, and you say then execute this, right? And now see what this returns, right? It returns a mono. What mono? It returns the same thing as what is returned by what you supply to it, right? So whatever the return value of the save is, it's a mono, will be returned back by the then, right? So we want to return whatever reading we saved, right? So this is going to return that mono. I'm going to simply say, instead of all of this hassle, just return this, right? And this should return a mono of readings. What is the problem here? Okay, that there is a problem with the readings class itself, which we'll come to later, but this is the reactive pipeline and the way you would do things with it. Now, again, this is a cold stream that nobody has actually started this pipeline. So this .vehicle.map, this hasn't been started yet. So how do you start it, right? We don't actually start this unless you were to manually write subscribe. So if I were to do subscribe, right, what I'd get is a reading, and then I can for instance just say system out println of reading, right? But as soon as I subscribe to this, right, it is going to return a reading. So this is not, of course, not blocking. You're waiting for that reading to come in as soon as you subscribe to it, and whenever that that thing comes in, you're going to print it. So instead, you can have a reading being returned here and block until all of this comes back and return that reading back to Netty. But in this case, what we're doing is we are returning a mono, right? So we are returning that cold stream back to Netty, and then Netty will do the subscribe part for us, right? So we don't need to subscribe here. But again, the concept is that you can subscribe, and in most cases within the application, there will be points where we do subscribe and get the information, and then process the information accordingly. But with the REST API, the concept is you give the stream back to Netty, and then the server subscribes to it and returns the results back to the client. So that is interesting. And we have add readings. Let's just quickly change this as well. So list of readings will just be a flux of readings. And then again, this will also be a flux, right? And did we not change this? How did we not change this? Okay, flux. Okay. Let us see if there's anything else. Reading service. Okay. So the next thing is to change the models a little bit. So just this thing where we're going to go into our models, and we cannot use the persistence anymore. So entity is not actually required. Everything remains same. ID, you're going to use it from Spring data at BBC again. Everything again, as I mentioned, remains the same. You don't even need to annotate it with an entity anymore. And then also let's change this. And ID. Okay. What else? What is the problem here now? Okay, just the interface then. Flux, and then again mono, as I mentioned. And flux again. Yeah, so there we have it. That is a very simple conversion from a regular Spring Boot project into a reactive Spring Boot project. And I know it isn't going to be this easy to actually migrate from a regular production scale project to do this, but I just wanted to bring about the differences between the two, and you can see how similar they are in terms of the work that we do. Just that the paradigm of programming changes a little bit. You would program more in a way that you would with a Java 8 application rather than with Java 7, right? So more of lambdas and stream operations and stuff like that, treating stuff as data streams and not just objects anymore. And let's run this. And actually, did I change the Swagger in this? I did, right? Yeah. Let's run this again. Look at Swagger and see if it is running. Okay, failed to start. Configure connection factory. Yeah. So this is interesting. What of course I forgot to talk about this, and this is. If we go into application properties, these are properties for Spring Data JPA, right? You don't have to configure a data source with Spring Data JPA because Spring does that configuration. You just have to provide the properties to it, right? And the properties are here. But with R2DBC, it is not mature enough right now for Spring Boot to configure the data source by itself and you give the properties and things happen magically. That doesn't happen right now. So we have to configure the data source, and that is what we're going to do. So here, I'm going to quickly configure the data source. And I do have a reference to do that. So let's say there is a class dbconfig, and what we're going to do is create a bean, of course. The bean would be of type Postgres SQL connection factory. right? This is coming from the R2DBC connector that we did in the Gradle file, right? We're going to say connection factory, and then we're going to return a new Postgres SQL connection factory. And then this takes in a builder object for a Postgres connection configuration builder. So we're going to say builder dot, we can pass in our host, which is localhost, of course. And then our database and what that looks like. So the database is Postgres. I'm using the default Postgres database. I did not create a new one. And then username is going to be RF Lafani. That's my username. And then password is I don't use password. That is bad. Shouldn't do that, but it's a local machine, so nobody cares. That is your bean, and also we have to mark this as configuration. So Spring actually executes this and does not forget about it, right? So configuration, and then let's try to restart this application here to see if it works now. Okay, it started. Let's quickly check Swagger again. Cool. We have Swagger running. Let's try to get the list of all the vehicles again, and we do have the list that we previously stored. So that is good. And then yeah, that is basically the demo, guys. There's not a lot to talk about here, but Praveen created this website back in the day where it used to mock values for these vehicles. So if I were to send readings from in here, the database will start accepting those readings, and for some reason they stop, so there's a backend error somewhere. But yeah, so let's check what this is. Row ID does not exist. Yeah, so these have to be inserted. It is trying to send readings for VIN numbers that are not already present in the database, and that is why it is failing. But yeah, I think that sums it all up. Let's get back to the presentation and discuss a few more things before we stop. So just give me 1 second to set the presentation back up again. Okay, we're back. All right, so we'll talk about takeaways. What is that we learned today? It's that Reactive is better, and there is a detailed article that I've linked here, which we'll go to here in a bit, that compares the different tech stacks, as in what is the throughput, efficiency, latency between WebMVC versus Webflux, R2DBC versus JDBC, stuff like that. And then you guys are able to see my screen, right? I just got a Zoom notification saying participants are now seeing your screen. So, okay, cool. Now, no need to worry about the lower layer reactive abstractions with Spring Boot. Spring Boot, as we just saw, gives us an amazing underlying API of reactive stuff. So you need not necessarily worry about how the thread configurations and asynchronous stuff works in the lower layer. It's all an abstraction to us as application level programmers, but you can still get all the benefits of it. So that's great. We can of course scale more with the same number of resources, and hence we can save a lot of cost on cloud, right? Because again, we are using the CPU to its fullest, CPU being the most precious resource in the cloud world, right? It's the most expensive as well. So the only problem that right now exists with going reactive is that it's still in its early stages, not as matured as something like Spring Data JPA or other Spring projects, right? So if you are going to step into that territory, be cautious about not being able to find as many answers on Stack Overflow as you would with the other projects, right? And yeah, that's it. It's not as mature as you would like it to be right now, but early adoption now means would be experts in the upcoming years when this technology booms, right? And then thank you, Note, for everyone who's helped here. So, of course, thank you everyone who's attending today. Great to have you guys all here. And then Praveen for organizing this and putting everything together, of course. And then Josh Long. Josh Long is a guy that works with the Pivotal Spring team, and he has got amazing content out on YouTube about the reactive programming stuff. So this kind of was a push start session. If you want to go into more details about how to use the reactive programming in real life scenarios, watch this guy's videos. He goes into pretty much all the details that there are to cover. Steve and Gagan are my teammates from the project that I'm working on, and there have been countless instances where they have helped me understand some of the basic concepts of reactive programming, and we've all worked on this and learned this together. So thank you guys. If you're here, thank you so much. And then we'll move on to any questions that hopefully I can answer. Yeah, that is pretty much it.
Hi, if I have a question. So first of all, yeah, it was amazing presentation, the way you describe at the very low level, kind of like much interesting. So my question is, definitely you have explained it in your presentation about the non-blocking calls, right? So the way I see it, if we have to work, or if we're gonna have to work with any of the servers which provides this non-blocking mechanism, that means that in order to achieve that level of concurrency, we might have to play with the objects that are kind of like immutable, correct? So so if the object is immutable for long running operations, for any sort of like any business operation which is kind of like long running, how would we achieve that specific level of separations when it's come to the concurrency, even with the immutable objects? And let's say if that specific business operation requires us to play with the objects itself, which would require us to make those specific objects as non-immutable. So in that way, definitely the first way would be to make the whole object as a synchronized block. But what other features does usually Spring provides in order to handle that specific situation for? Mm-hmm.
So I think I get the question that because it's the multi-threaded programming world, it's better to have immutable objects so that there is no problems with the asynchronous aspect of it, right? But that's the beauty of Spring and Webflux, right? The lower level API takes care of handling the synchronous part. You don't have to worry about it. Not necessarily you have to have your objects immutable. You can have mutable objects. You can change the objects as in a way that you want, provided you follow the guidelines from the Spring team on how to use it. So once you start using the Spring Webflux framework in the right way, you understand the Project Reactor basics. You don't have to have the objects immutable to work with in the multi-threaded environment. So you can still have all this reactive benefits and still do all your business logic with mutable objects. And not worry about immutability, of course. So that again is very beautiful that Spring has done stuff for us. And this is again part of the Project Reactor. Every operation within Project Reactor is non-blocking, and it helps you work with mutable objects as well.
Sounds good. Mm-hmm. Thank you.
Thank you for joining me.
Yeah, hi, I have one question. So so does this reactive programming will serve the asset property for the relational database as well? For NoSQL, it's pretty good, but for the because we are now talking about the relational database, does it serve asset properties?
Yes, so the R2DBC driver that we talked about, and actually let me go back here and open this link as well. Yeah, so I'll talk about this link. But to answer your questions, yes, the asset properties do apply. wherever necessary. That you can do transactions as well with Reactive. So the other thing that I did not cover in this demo is that within the service or within the repository, I know you could do. Okay, I'm not sharing my the screen, but I was actually going into the project and going to do the add transactional. So with R2DBC, you still get the add transactional that you used to get with Spring Data JPA, and you can do transactions on a class level or on a method level, and all the asset properties apply. And how does that happen with asynchronicity, right? How does that happen with non-blocking IO? Again, the answer lies within the framework. So R2DBC does that for you as application level programmers. Again, we have the benefits of not knowing it all and still being able to use it. So it's an abstraction for us. The R2DBC driver has now support for many different databases. Postgres, as we just saw, was announced recently, but all the major databases are now coming up front and working with the Spring team to develop this driver that is non-blocking for their databases. So it's not just the Spring team that is in an effort to develop these drivers. A lot of companies are volunteering to actually work with the Spring team to come up with drivers so that the non-blocking fashion can be supported for their databases as well.
Yeah, that's answered my question. Thanks, Arif.
Thank you.
I had another question if you have time.
Sure, Raj.
Yeah, so like just like it may sound a little dumb, but like if in how does Jackson kind of behave with Flux in a way? Like if I had do I need to have a Flux inside an enclosing object, and does Jackson kind of treat it as a list? Or do I need to kind of, for example, like if my repository is returning a Flux, right, and I want to enclose that in an object as a list and return it back to a client, how?
Yeah. So the basic concept is that you cannot have a publisher wrapped into a publisher. So you cannot have a flux of Flux, or you cannot have a flux of mono being returned back. You do a flat map and convert it into a single list. Now, if you want to return a list back to the client, you would use Flux, right? And I think the framework internally interprets what sort of return the client is expecting, and then converts that Flux into a list. And I'm guessing stuff like hash map and stuff. What would you do there, right? But for list, I'm sure what you do is return a Flux. I'm just thinking about complex collections that I haven't gotten into yet, I think. So if you were to return a complex collection, how would you do that? Just a second, let me share the other screen where I have this comparison open as well. So this is the comparison that I was talking about. But Raj, to answer your question, I am not sure about complex collections. If it's just a list, it can be a Flux. And if it's just a single object, and Jackson will work. So Webflux has Jackson internally, right? Of course, the parser has to be there. So Jackson works flawlessly with Webflux. And for list, I'm sure for hash maps and complex collections like that, I'll have to take a look into what's really happening there. But to coming to this comparison, this guy has done a comprehensive comparison of all sorts of different combinations. So he's done WebMVC with JDBC, WebMVC with R2DBC, Webflux with JDBC, Webflux with R2DBC, and he's measured response times, throughputs, process CPU usage, memory usage, and all of that stuff. I'm going to take this link and post it right here in the chat box if you guys are interested. And if you go through it, you can see evidently Webflux and R2DBC come out on top all the time. It's not in one or two situations, they come out on top all the time. So yeah, basically using R2DBC and Webflux is good for us.